Hi, good morning, everybody. I'm so excited to be joining you there in Sydney, remotely here from Atlanta, on the occasion of the first ever remote plenary talk at ICP. And I'm very grateful to the organizers for this opportunity and excited to see a reflection of the sign of our times, as well as a vision of how we might evolve to reduce our flying as a community. And I am happy to say I've finally overcome all of my OCD tendencies in taping and retaping this talk for you today. And here's to this being the last version. So without further ado, let's get started. And first, I wanted to acknowledge the amazing contributions of my former graduate student, Pam Groth, who's now at University of Mary Washington, who really generated the vast majority of the data that I'm going to show you today, and as well as a whole number of students who have come through the Cobb Lab over the years here at Georgia Tech, and some longstanding collaborations dating back to my dissertation work. So this is a fossil coral rubble field on Christmas Island, and we'll be talking a lot about samples like this in the talk today. First, I wanted to call the Great Pacific Ocean into the room. And this is obviously something that's near and dear to all of our hearts. It covers half of our planet, so it's near and dear to the entire climate system as well. And this is a particularly beautiful image showing 4 different tropical storms making their way across the basin in 2014. And of course, that vast expanse is one of the reasons why I opted not to travel to Sydney for ICP. So as much as I miss you, I am happy to be avoiding the emissions of over 2 tons of carbon dioxide associated with that trip. If I had gotten on that plane and flown to Sydney, I might have been able to look out the window and see the Northern Line Islands underneath, and those are the island chains that we've been working on for 20 years here at Georgia Tech and previously at Scripps, building up an archive of past climate variability from this very data-poor region of the world. And of course, this is also an important region of the world for the climate system, being home to the El Niño Southern Oscillation phenomenon. It probably needs no introduction in this group, but this is a coupled ocean atmosphere phenomenon that comes and goes every 2 to 7 years. And these very warm temperatures that you see here across the equatorial Pacific drive a reorganization of the entire global atmosphere and are responsible for temperature and rainfall extremes across the world. And as you can see here from this dot in the middle of the basin, we're dealing with some sites that are heavily impacted by the phenomenon. And that's why we've been working there for so long and building up an archive that we've collected there and a lot of data about how El Niño impacts these sites. So dating back to 1997, which was my first research cruise down to the equator from Honolulu on the Moana wave. And Rick Fairbanks was the PI. And we were basically going down in the middle of what was to become the largest El Niño on record, October to December 1997. And so from that moment on, really, I was very, very intrigued by the variability that El Niño exhibited in the late 20th century, coming off of 2 very strong events, as well as, of course, now this question has become really important on the heels of the 2015-2016 event, which had its own devastating consequences for ecosystems and communities across the world. And so the idea of understanding how ENSO is responding to anthropogenic forcing is important for implications of climate change, but it's also unfortunately really difficult to address with the available data that we have, whether instrumental data, but also paleoclimate data, because we need long, really high resolution records to look at this question, and those records are still few and far between. So looking at the consequences of El Niño on Australia here close to y'all, you can see that El Niño has a very profound impact on Australian rainfall patterns, driving pretty significant deficits in rainfall across the eastern portion of Australia. And this is something that caused a very, very profound and widespread wildfires across Australia during the last El Niño in 2016. This is a particularly devastating shot from Tasmania, where wildfires are raged out of control for a good portion of the season down there, and decimating some very unique and special forests. Of course, it's not just the wildfires and above ground effects that we have to worry about in Australia with El Nino. This is a depiction of coral bleaching and mortality across the Great Barrier Reef in Australia. Obviously an iconic feature of our planet. And during the very protracted, very severe warm ocean temperatures during the event, much of the northern reef experienced bleaching and some degree of mortality that spread all the way across to the southern portions of that reef as well. And it's not just in Australia that happened. It actually happened all over the globe across the tropical ocean belts. You may remember some of the news coverage here. And this was across the Indian, Pacific, and Atlantic. And I'm highlighting in the middle of the plot there the circle denoting the location of the Northern Line Islands, which also took a very serious beating during the 2015-2016 El Nino event. We'll come back to that. This is all really seminal work by Terry Hughes and his colleagues at the ARC Center of Excellence for Coral Reef Studies through a series of papers that continue to raise the issue of the threat to coral reefs from climate change and its intersections with warming trends. So the real irony of the situation is that we're going to be using the Coral Archive itself to reconstruct ocean temperature extremes associated to El Nino events. And so here you can see me scuba diving on the reef at Fanning Island at 4 North. And we have a very large hydraulic drill and my trusty drilling assistant, Jordan Watson, there. Coring a coral core, in this case, that's going to take us back about 50 years in time and enable us to build up a record of how the modern El Nino activity at these sites have impacted the coral skeletal geochemistry and isotopic signatures. And then, of course, we're going to push that back in time as well. And so the whole goal of the work in our lab is really to understand how ENSO has varied in the past prior to the rise of anthropogenic emissions, and what were the responsible drivers for that variability. So we can think about both external drivers like volcanic and solar forcing, as well as internal climate drivers, changes in mean state, changes in different temperatures across different ocean basins, etc. All of this is of interest, but today we're really going to focus in on the anthropogenic question. So we're going to use two different archives to address this question. One is the Living Coral Archive that's growing on reefs today across the tropics. And this is a kind of coral that we use called Porites, and it grows roughly 1 to 2 centimeters per year. We drill it by scuba, and it takes us back anywhere from 50 if it's a shorter core, all the way to 400 years in the case of the longest cores that have emerged from the Great Barrier Reef. And so in working with corals for climate reconstruction, it's important to recognize the role for Australian scientists and Australian science that has been conducted on the Great Barrier Reef for decades now, that provides the foundation for everything that we do in coral paleoclimatology. And so the Great Barrier Reef, again, iconic contributions from there. Moving over into the fossil realm is really what we're going to focus on today, the expansion of this approach to fossil corals that are scattered around ocean-facing beaches all over the tropics. And of course, these are samples that we can collect any number of different ways, drilling or by hand. In all cases, we're going to need to uranium-thorium date them to understand where in time they fall. And then, of course, we can apply the same kind of techniques that we apply to the modern corals to understand the record of climate variability that's locked in those skeletons. And so in order to do that, we look at the coral oxygen isotopic composition of the coral skeleton. So here on the left, you can see an actual picture of a coral core complete with a organic tissue layer at the top, and a transect that we've laid down the growth axes that are in turn revealed in the X-ray image that I'm showing there as well, that helps guide our sampling and provide some chronological constraints through, in our case, very faint annual banding. And looking at how the oxygen isotopic composition works in the coral skeleton. I don't think we need to belabor this point on Friday morning at ICP of all places, but the coral oxygen isotopic composition is a function of the sea surface temperature in which the coral grew, the delta 18 of seawater, which is in turn reflecting changes in the P-E balance of the surface ocean, as well as a regional hydrology and hydrography of how ocean circulation is moving water masses around with different properties. And so to a first approximation, you can think about it is tracking sea surface salinity very closely. There are some very interesting nuances to that statement, but you can go back to some foundational literature with Rick Fairbanks in 1997, all the way up through some more current work by Jess Conroy and colleagues looking at the distributions of the modern ocean in relationship to salinity. I point you to those papers. And then last but not least, we have to recognize that we're dealing with a biological archive that has its own quirks and limitations and overprints. And so we can encapsulate this in this kind of epsilon term, recognizing that this is reflecting calibration residuals with SST, some of which we don't understand, as well as coral to coral to coral offsets that impact the reconstruction of mean climate from single corals in particular, but are not as impactful in terms of impacting the El Nino reconstructions, which are focused on relative variations within a single coral skeleton. So the whole goal of our lab is to really beat back that uncertainty term, all of its pieces, with a very, very high degree of replication, which is what I'm going to show you today in the distribution of samples over the last 7,000 years. And so at our sites in the Central Pacific, during El Nino events, we have a pretty good fit to the proxy that we're just walked through. So during El Nino events, it obviously gets very warm at the sites, as illustrated by the top panel of sea surface temperatures during the 2016 El Nino event. And on the bottom panel, we're looking at outgoing long-wave radiation, reflecting the shift of convection from the Western Pacific to the Central Pacific Ocean. That's going to alter the surface balance of P-E and drive oxygen isotopic composition of the surface ocean down. So both of these impacts are driving coral oxygen isotopic values down. And so during El Nino events, we have a compound signal when we have warmer, wetter conditions, and during La Nina events, the opposite happens when we have cooler, drier conditions. And so my thesis today is that we have a really good fit between the right proxy in coral oxygen isotopes in the right place in the Central Pacific, looking at El Niños, and then at the right time step, meaning that we have the resolution to bring to the problem of El Nino reconstruction, which really requires at least one sample per month if you can get it, because in some cases El Niños can come and go in 6 months. And the more resolution you have, the more you can resolve those interannual events. And so looking at the calibration that we've amassed to date, this is the work of decades of analyses and dating back to seminal work by Mike Evans for his dissertation previously published in 1998-9. And building on that, you're seeing 8 different coral records in colors spanning the last couple decades here. And you're also looking at IGOS SST in gray, which is underlying those records. And the point here is that you can really see that the frequency and amplitude of individual ENSO extremes on the warm and cold side are well reproduced in these coral records, and that there's, in fact, a very high degree of reproducibility among this ensemble of coral records up to and including the 2015-16 El Nino event. When we look at what is causing the excursions in coral oxygen isotopes with respect to the contributions I outlined before, I'm going to take a deeper dive on 2 of the recent El Nino extremes, 1997-98 and 2015-16 here, through some amazing work by my former undergraduate researcher, Gemma O'Connor, and using some in situ analyses of water from those sites at those times of extremes, as well as some logger data collected across those extremes. And so this is what we're doing. We're looking at the 2 events stacked up together. On the top is an ensemble of coral oxygen isotopes analyzed across as many cores as we could get our hands on that cover that time period. And the second level down is in situ temperature. So many cases, these are loggers that were deployed, but also include some satellite blended products and Togatau buoys. The next step down are salinity bottles that were collected during these expeditions, pegged at those maximum time windows, as well as some CTD data that we had deployed at Christmas. And then on the very bottom, you can see the Delta 18 of seawater collections that were done by bottle and analyzed subsequently for the delta 18 of seawater. And so the main point is that through these kinds of detailed investigations of these specific extremes, we can determine those contributions to these extremes from the different components that we expected. And not to go into too much detail here, but the bottom line is that Gemma's work helps us understand that no less than 80% of the coral oxygen isotopic signature that's locked into the corals during El Nino extremes here is related to sea surface temperature, and no more than 20% of the coral oxygen isotopic signature is related to the seawater changes in delta 18. And so that's a really handy number to keep in mind for later, and really highlights the outsized role that sea surface temperature anomalies play in driving the observed intraannual variations in coral delta 18. And so when we go to push this back in time, we're confronted with a deposit like this. This is Christmas Island, a rubble field. Many of you in the audience have toiled alongside me on these rubble fields. I thank you for that. It's not easy work, but you can walk down the beach like this and pick up a sample that's 5 years old, and right next to it can be a sample that's several thousand years old. And so we do a kind of a high-end approach and collect as many good samples as we can find, bring them back for dating analyses and dating screening, most of which is presented in Pam Groth's 2016 paper in G Cubed. If you're interested in how those dating distributions map across the island, I am not a geomorphologist, but it's very cool to see the different dating distributions on these beaches and to help them inform our sampling when we want to go after a given interval in time. Fun work, rewarding work, but very hard work. So looking at what we've amassed over the last 20 years of work at these islands, you can see that we're working across the 3 islands in question, Palmyra, Fanning, and Christmas. We've conducted over 13 expeditions to these research sites through various boats and planes. And we have collected over 20 tons of different coral. Some of it is still on the island. A large portion of it is here at Georgia Tech. Some of it's back at Scripps. And a representative piece here is pictured as an X-ray from one of our more recent, younger fossil coral samples that we collected for a project led by undergraduate researcher Nick Hitt, now over at Wellington. And Nick, I believe you owe me a manuscript. But at any rate, very exciting to have amassed so much material to work with. And in moving through that, we've worked on and analyzed over 2,000 radiocarbon measurements, over 500 uranium thorium dates, and over 100,000 or more delta 18 samples that we've analyzed for the monthly reconstructions I'm going to show you in a minute. Most importantly, we have engaged over 20 students in the lab over this time period, including undergraduate researchers, graduate students, and some amazing postdoctoral scholars and fellows who I had the deep honor to work with, some of whom are probably there today. And so all in all, we've amassed about 2,200 years of information, all monthly resolved, from these very data-poor sites that help us understand the past history of ENSO variability in this key region and what are its important drivers. And so this is one such record we've been able to amass as a result of these decades of work. And so this is a stretch of data that spans roughly 300 years in the earlier part of this millennium. And you can see 8 different coral records here, anchored by their corresponding uranium thorium dates and kind of tied together where they overlap, showing very high degree of reproducibility. And across that whole sequence now, which is all monthly resolved data, you can see the coming and going of El Niños and La Niñas. You can see longer term decadal scale variability, as well as some century scale variability locked in this sequence. And so the question for us today is, how do we take a sequence like this in all of its richness and distill a metric from this that's going to represent for us the strength of ENSO variability in a sequence like this, and basically find a way to plot and synthesize the ENSO variability across the entire archive into a single plot and bring some analyses to it. And in doing that, we're going to introduce the methods that we use to extract that ENSO variability from these monthly resolved sequences. The first thing that we do is we apply statistical filter so that we can pull out the intraannual component of variability. So either a 2 to 7 or 2 to 8 year bandpass filter typically. And then we're going to apply a 20-year moving window through that filter time series that's going to look at the standard deviation of variability in the intraannual band as it evolves over this entire sequence. And third, we're going to take these estimates of standard deviation in these fossil coral sequences and compare them to the corresponding interval of the modern coral sequence in the late 20th century that runs from 1987 to 2007. So that's our chosen benchmark for quantifying the relative changes across the entire fossil archive of ENSO variability. And so we chose that interval because it is the most recent interval for which we have all three coral records available from Palmyra, Fanning, and Christmas Islands. And so it's also an important interval for thinking about the potential role of variability in the late 20th century versus the pre-industrial era as a whole. And so with that information, we're going to be plotting all of the coral sequences on a plot where Palmyra fossil corals are benchmarked to the Palmyra modern coral. Fossils from Fanning are benchmarked to the Fanning modern, and Christmas fossils are benchmarked to the Christmas modern. So we have an apples to apples comparison across our entire archive, and we're going to be reporting that all in relative terms, all to the same late 20th century benchmark in the next plot. And that is what you're looking at here. This is work that's under review by Pam Groth. And so here is the plot distilling that information from the three islands. We have Palmyra in red, Christmas in green, Fanning in blue, and this is not an even dating distribution by any means, as you can see here. But moving over to the right-hand panel, I want to draw your eye to the treatment of the modern corals there from the different islands. So these range in length from 80 years to about 130 or 40 years right now from the different islands. And you can see how the standard deviation of ENSO in those 20-year bands evolves across this modern coral length. And so if we look at what we're depicting here, we're showing the utmost tick mark on any given point of a coral sequence actually represents the 20-year window in which that sequence had the maximum amount of ENSO variability. And then on the very, very lowermost indicator there, on that vertical stretch, you have the ENSO variability for the weakest 20-year interval of that given coral sequence. And so the center dot represents the mean for that entire coral sequence, with the absolute min and the absolute max and absolute min of the range of ENSO variability as measured in a much, much longer coral sequence. So the gray bars going through this plot are denoting the kind of spread of modern coral ENSO variability that we see in the instrumental era, but as documented in the modern corals. And then if we go back to the fossil coral plot, now we're going back 7,000 years of information, and we have these different windows through time. The size of the dot represents the size of the sequence, and so the really long sequence we just looked at from the early part of the millennium at Palmyra is that huge red dot, 320 years worth of information. So obviously we'd like that to talk more strongly to us when we assess the variability in this plot. And so on the y-axis here, you have, again, that relative percent change in the standard deviation of the interannual band in the corals as a relative to the 1987 to 2000 interval of the modern. So if you're higher than that dotted line, you're going to be exhibiting higher ENSO variability than the late 20th century benchmark. And obviously, negative numbers are lower relative to that benchmark as well. And so looking at what this data is telling us with respect to the question at hand, it's an important observation to make that most of the fossil coral data are falling below that late 20th century benchmark. Not all of the data are falling below that benchmark, but the vast, vast majority of them are. And so you can see in the last millennium, especially for those Palmyra sequences there, you can see that there are some 20-year windows that are actually exhibiting stronger ENSO variability than the late 20th century. But the vast majority of those sequences, of course, are plotting below the red line. And so this really raises the question about whether this is a significant change in ENSO moving from the pre-industrial into the late 20th century, or whether this is just the result of undersampling what we know to be a highly variable system. And this is just a scatter shot that's, we've tricked ourselves into thinking that this is a significant shift in this data from the pre-industrial to present. In order to test that and develop a framework for assessing the uncertainty of that sampling, we're going to have to build a pretty serious null hypotheses and do some Monte Carlo simulations to understand what sampling does to our potential distributions when we have so little data over such a rich system. And so in that case, we're going to be looking at constructing a null hypothesis that allows us to sample many, many millennia of El Nino variability in all of its richness. And then we're going to be subsampling that data set and matching the coral data set that we have sequence by sequence by sequence, and the length of those sequences matched as well through time, and then bundling those into a pre-industrial set of data and a 20th century set of data. But in the case of the null hypotheses, those are all pulled from a stationary system. And then we're going to test to see whether our observed distribution from the real data set is actually consistent with any of those ensemble members from the null hypotheses, or whether we can infer that there's been a non-stationary shift in ENSO properties that our data set is capturing. So we're going to use two different null hypotheses for this work. Number one is a statistical model of ENSO evolution, a linear inverse model that basically reflects the fundamental characteristics of spatial temporal variability in the late 20th century. So it's trained on the last 50 years of data. And then it's also stochastically driven. So it's allowed to wobble in a phase space, if you will. But at the end of the day, any given sequence, the properties of that sequence over long enough are going to converge onto the properties of late 20th century and El Nino variability. And so we have 20,000 years of Niño 3.4 SST index from that, because it's a fairly cheap system to run, being a purely statistical model. And the other null that we're going to use is a dynamical model, in this case, CESM, where we are employing the Last Millennium Ensemble published by Betty Otto-Bleissner et al. And that is 10 realizations of 10,000 years each. Again, looking at that Niño 3.4 SST time series in both cases. And so these are our nulls. These are our realizations of a stationary but rich spectrum of ENSO variability that is plausible representation of the real world. And then we're going to be sampling that to see if we can reproduce the observed shifts in ENSO variability from the pre-industrial to today. And so these are the distributions that emerge from those two nulls. On the left, you have the statistical model null, and on the right, you have the dynamical model null. And in both cases, you want to look for where that green bar of observed variability, which was the 30% shift from pre-industrial to the late 20th century, is falling with respect to the 95 and 99% confidence intervals for the chance results of various variance changes that can result from a stationary system that is undersampled. And so in both cases, you can see that we're exceeding the 95% confidence interval for variance changes in that stationary system. And this would be consistent with the statement that there actually is evidence in our coral data set for a non-stationary influence or non-stationary feature of the ENSO variability across our entire time series. And so in our case, we would hypothesize that that is related to anthropogenic forcing, and that there may be a role for anthropogenic forcing in driving an intensification of ENSO variability in our site. And so obviously we're going to have to pull from any number of different lines of evidence to wonder whether that is consistent across available records and finds any dynamical support amongst models. And so looking first at the paleoclimate records that we can bring to bear on this question, there have been some very important advances made over the last 5 years or so, starting with a long 700-year reconstruction by Lee et al. In 2013 that did find a significant increase in recent ENSO variability as compared to the entire rest of the reconstruction. Moving on to Shane McGregor, again, pulling together a range of multi-proxy reconstructions and single records and looking at how the variance evolved and concluding that there had been a recent uptick in ENSO variability relative to the previous centuries. And in this case, I'm also lifting up a paper by Liu et al. In 2017 that I was involved with, focused on looking at 14 different long tree ring reconstructions from Taiwan, in this case using cellulosic oxygen isotopes as a proxy for larger scale hydrological changes that related to El Nino. And so I'm plotting that result down on the bottom there, where you can see that across these 14 different realizations of tree ring data from Taiwan, you can see an uptick in the interannual variability for the last portion of the data set relative to the average for the remaining 700 years. So these are the kinds of proxy information that help us to understand that there's an emerging signal there. And last but not least, there's some work that just came out earlier this year by Mandy Freud et al. That looked at a multi-proxy coral reconstruction of ENSO variability in the tropical Pacific. And on the bottom, you can see their results, primarily indicating that over the last 400 years or so, they're documenting an increase in the frequency of Central Pacific El Nino events. So that's the flavor of El Nino that is, the warm SST anomalies are confined largely to the Central Pacific, noting an increase in the frequency of those events coming into the late 20th century. Very consistent with our results, of course, from the single site that we have. And so looking at whether this finds any dynamical support out there and what might be the explanation for this body of paleoclimate evidence, looking at anthropogenic influences on ENSO properties, we find three potential different explanations. They can all be contributing, or it can be some maybe more important than others, but there is some evidence that we have to consider the possibility that anthropogenic forcing is driving an increase in the sea surface temperatures in the Central Pacific, so favoring that Central Pacific El Nino mode. Again, most of that work was done with CMIP3 models. We'll have to see what CMIP6 says. There is some work with CMIP5 models that just came out by Chai et al. In 2018, looking at the phenomenon more broadly and noting that in CMIP5 models, moving from the historical period into the 21st century actually sees an increase in the standard deviation of the ENSO phenomenon itself. So that is quite significant with a much more broad scale change in El Nino SST amplitudes. And then on the bottom, last but not least, is something that's been quite well documented across CMIP5 models, is looking at the fact that during a warmer world, you actually can expect a larger hydrological impact related to any given ENSO-related SST anomaly. And so you can kind of think of this as more rainfall bang for your SST buck. And in this case, looking at the sites involved, it's important to recognize that every single proxy record that we have is indeed influenced to some extent by hydrological variability associated with El Nino extremes. And so this is a very plausible influence on our collected data sets as well, and may explain a portion of the signal that we're seeing with the intensification effect. Now, from our site's perspective, we have some evidence to support the idea that we cannot ascribe the recent intensification of El Nino at our site purely to the hydrological response, because there's just not enough room in that contribution, as evidenced by our calibration work across these last El Nino events I showed you earlier. So again, a maximum of 20% allowable for that hydrological component at Christmas Island, and this observed shift from the pre-industrial into the late 20th century coming much closer to 30%. So while there may be a contribution from this greater rainfall bang for your SST buck, we also think that we are able to support some evidence that the underlying SST anomalies themselves have been increasing in amplitude in the late 20th century. And so I'd like to kind of circle back to this key question and think about that I posed earlier that's been driving force of a large portion of our lab's research is ENSO changing, and say that yes, I think there is a body of work with multiple lines of evidence coming out in the very recent years that supports an anthropogenic influence on ENSO properties. And certainly there's a big asterisk there because the AR6 will be combing over this and also including some of the CMIP6 work that is just beginning to get underway in earnest right now, and may provide a more definitive statement than my own view of this matter. So stay tuned. So what I want to pivot to right now, though, at the latter portion of my talk, is to step back from this very kind of scientific, fascinating question, one of the most difficult questions in climate science, something that has driven so much of my research agenda, and say that, well, now that we've provided, I think, from the Line Islands at least, the best possible answer that we can provide from the Line Islands, kind of ask ourselves, okay, you know, does it really matter that we may have provided the next piece of incremental knowledge to drive that question's answer, the next step? And I'm going to look at this from two different perspectives. First, thinking about impacted communities that live in ENSO vulnerable regions. What are they facing, and what do we have to keep in mind as scientists in terms of delivering what they really need? And in doing this, I want to recognize that the communities that I've been working with for 20 years are extremely vulnerable to ENSO extremes. And this is a plot of the coral reef before the large El Nino of 2015-2016 on the left there. And you can see me installing a CTD on a very healthy reef. And then after 10 months of bleaching level temperature stress on the right here, you can see that most of that coral is just an absolute wasteland. 85% of the reef died over 6 short months between expeditions. And so that's the same exact site, just absolutely devastated. And so we might remind ourselves in this case how important these ecosystems are to vulnerable communities all over the world in terms of ecosystem services. And in doing so, we need to remember it's not just an El Nino event that is threatening them with climate change, but there are any number of chronic stressors that are becoming more acute for these communities all across the world, including changes in baseline temperatures that are making any given El Nino event much more impactful and damaging to their communities and ecosystems, but also as well as remembering that freshwater resources are often a major challenge for these communities, and those larger scale hydrological patterns are probably also changing in response to climate change. Unfortunately, in many ways, we actually don't yet fully understand because we don't have very good long records of these potential changes and how they can be separated from decadal variability. And so I want to recognize that there's a major role for the paleoclimate community to play in developing those kinds of data sets that span the last 200-300 years. And in doing so, I'd like to recognize an effort called Coral Hydra 2K that Thomas Felix will be talking a little bit more about later. And we're collecting a whole body of folks who want to get to work on the available archive, add in any new data sets that they might have available, and look to parse out the influences of temperature on these coral records and separate that hydrological component out and see what most broadly we can say about the anthropogenic related trends across the tropics in temperature and hydrology. So stay tuned for that. I think that's important. The other piece to recognize, though, is that the does it matter question doesn't start or stop with science. It actually includes a reflection about our role as scientists in this era of accelerating climate change. And we could ask ourselves, what is our own personal tipping point with that question? As we see the latest indicators of climate change accelerating all around us, as we see the election of officials who are not ready to enact data-driven policy, and who are operating under the influences of deeply vested interests. What is our role as citizens, as scientists, as academicians, as an institution of higher education? And in doing so, we might think about the notion of tipping points for us personally. And I can definitely say that my tipping point was reached in 2016 when I was diving on these reefs in the remote tropical Pacific, and they were mostly killed by this El Nino extreme and the ongoing warming of the tropical oceans. And at the same time that I was diving on those devastated reefs, the United States was electing an administration that was openly hostile to climate science and data-driven policy in that area. And so personally, that was my tipping point. And I decided to do quite a few things quite a bit differently, starting at the AGU in December of that year, where I participated in a Stand Up for Science rally to remind the scientists around me that, we have a responsibility in this era. We saw it coming then, and now we can see many of the fruits of efforts to dismantle and refute and marginalize scientists and scientific data across all sectors of the federal government. And this is an effort that we must stand up against and fight for our data and the facts that they support, and really try to make sure that we can play an active role in this. And in doing so, we need to recognize the powerful will of collective action here. And that when we stand up together and we lend our voices to this problem together, we really have a chance to make our mark on history. That, I think, is very clear at this point. And beyond that, we also can think about our roles and responsibilities as citizens that are ultimately oftentimes quite privileged and hold quite powerful reins in terms of moving the needle on collective action on climate. And so this kind of calls into the room a much larger sphere where we can think about this diagram of responsibilities on the one hand. So where do the responsibilities for emissions lie? Those lie with the most wealthy and most privileged sectors of the population. And then on the right here, the inverse relationship with impacts, which is those who are most wealthy and privileged are going to be cushioned and protected from the impacts of climate change, while those who are on the bottom of that triangle of the impacts, the global poor, are going to be acutely vulnerable to ongoing impacts of climate change. And so how do we reconcile that as individuals, and as individuals who ultimately are part of institutions that can be a very big part of the solution to climate change and this kind of structural changes that we needed? And with that in mind, I'm going to call into the room the discussion around flying less. And I know I can see many of you shifting in your chairs right now, and I can hear the nervous chuckles all the way here in Atlanta. But I think this is important to raise as an issue, especially as we sit in Sydney together, contemplating the next big ICP location and what we want to become as a group of folks who are engaged deeply in the issue of climate change and climate science. And while some people dismiss the Flying Less movement as fixated on nothing more than 2% of global emissions, or something that is derailing the call for collective action by focusing on individual choice, I'm here to argue that I think it's an important instrument, both personally. I find it very fulfilling and nurturing, and it unlocks a new level of engagement for me. I also recognize that when I did my carbon footprint measurements about 2 years ago, flying was over 85% of my personal carbon footprint. And that's not something I could unsee, especially knowing that the reef that I was just diving on in 2016 were devastated by warming oceans. These are impacts that we're now seeing all around us. They are impacting the most vulnerable among us, and they will continue to do so. And so with respect to what I can do, it's not the only thing I do, but one of the things I can do is try to move us along a conversation about flying less as scientists and academics who are part of the global elite that is playing a role here. Flying is also one of the fastest growing sectors of emissions, and one of those sectors of emissions that we don't have a ready substitute for. And so even if we could put a reasonable price on carbon, there would be no way to meaningfully move the needle on aviation with that. We just don't have the technologies, and the people who are doing the flying are not going to be sensitive to that kind of price point. And so this is really going to be something that's going to have to be handled a little differently. That's why I think it's an interesting conversation, and one that I think we can play a role in leading as scientists and leading as members of the higher education sector. So what might be some of the first steps? What might a vision look like? This is something that I think we can anchor as individuals blending into the collective action sphere. So I think there's room for both here, and I'm just noting a couple ways that we might think about that happening. One is to organize and request for remote and virtual participation in our conferences and workshops and invited seminars. We can think about taping and streaming the lectures. We can think about e-poster sessions. We can think about really cool hangouts in virtual spaces together, and virtual beers and coffees. Or we can also think about regional hubs that are actually groups of people getting together in places like Atlanta for ICP, and having their own kind of regional experience that are tied together and coordinated across regional hubs. That's, I think, an important vision to begin agitating for. Whether or not you take advantage of these pieces of infrastructure, ask conference organizers, and if you are an organizer, challenge yourself to take that next step that would move that particular series of meetings along the road to greater remote and virtual representation. The second thing is that if you do choose to fly less because of climate change, please talk about it. The conversation around flying is so polarizing. There's been people like Greta Thunberg who have brought up this issue to the international foreground, but in doing so, it's been framed as kind of an absolutist thing where you're either in or you're out. And that's not very constructive from my perspective as somebody who is still called to fly professionally on quite a few occasions and has personal obligations across the globe to different family members. But personally, I do choose to limit my flying, and I do choose to talk about it because part of the challenge is raising the cultural awareness around this point and beginning to shift the needle and recognizing that there will be increasing numbers of scientists who just are not willing to incur that carbon cost to maintain their professional connections. And we shouldn't have to. So we're going to have to build a different way, and part of that starts with a conversation, respectful with what people think about this and what it might look like, and what we have to benefit in terms of greater access and greater inclusion for scientists who can't afford to attend these fancy meetings, or parents who have family obligations as well. So there are many co-benefits here. Let's talk about it. Last but not least, there's a lot of debate around carbon offsets. I'm personally a big fan of carbon offsets. It's how I got into this kind of thinking and reflecting about my own flying footprint. And I note that I tried to do so in a data-driven fashion. And so there's a recent paper suggesting that the social cost of carbon, which is the amount of damage incurred by emitting a single ton of carbon dioxide today, is something like $418 a ton. So that would have added roughly $950 to my round-trip Sydney flight. And obviously that is a market signal to me, but it also allows me to put aside a set of funding to move the needle on projects that I think are moving us in the right direction at a collective level. So I give to my local tree planting organization, I give to preserve forests and their vast troves of carbon that they have sequestered, and I also give to organizations that promote environmental justice and climate justice, including all the amazing youth movements that we now see cropping up. I'm desperate for funding and resources. So, and today I wanted to lift up one particular organization that I think is doing incredibly meaningful work in this area, and that's 500 Women Scientists. There are pods all over the world, of course, and I'm happy to be a part of an effort called the Fellowship for the Future, which is an effort to fund women of color leaders in STEM to think about how they might be able to take the next step towards achieving their visions and goals around inclusion and accessibility in science. And so I'm very happy to be a part of that, and I encourage you to take a look at it if it makes any, if you're curious. And I also want to note that 500 Women Scientists is really dedicated to breaking down the structural sexism and structural racism that we have that hold science back and hold it from serving society in its highest potential. So this is something that is very, very relevant for climate solutions as well. And again, there are many orgs and different ways to get engaged with that conversation and do this meaningful work together. And so I would say to the question of does it matter, I would say categorically yes, there's no calibration language needed. You can think about your role as an individual. You can think about your role as a member of a community like a university. You can think about your role as a parent, as a daughter in your own family, and then of course as a voter in your city, in your state, and your nation. So we have many different roles to play. We have many different levers. There's a lot of need to lift each other up when we do find some ways to engage in this. And there's no wrong way to do it. And that's important because actually, of course, we are out of time and we need to find new ways to get this done. And we cannot rely on huge policies that may never come to be, even though we can fight for those every single day. But it's really going to be an all hands on deck moment, all of the above moment. Lastly, I wanted to thank all the amazing people that have made up my lab over the years. This is one of its recent iterations, and all of the people who have come through my lab bring such a diverse set of perspectives and lived experiences and goals and values and preferences that they enrich my lives every day. And they really help me remember that there's really no distinction between the personal and the political when it comes to these times. And there's also very little distinction between science and society in this era as well. And that when we explicitly recognize that those boundaries are very blurry and we welcome that into our lives as individuals, as members of universities and members of the scientific community, we actually have a path to create science as a much stronger institution, as a much more inclusive institution, and something that can reach its full potential in serving society. Thank you. Okay.